Right, so 7B today, we're talking about combining probabilities. So instead of just one event, what happens when we're looking at the probabilities when there's multiple things happening at once? So first things first. So this guy back in 1650, this con man, I can't even pronounce his name. He was betting other gamblers that he could roll at least 1/6 out of 4 rolls. And he made a profit. He won more often than he lost. Now, the way that he determined his probability, he said, well, I've got 1 in 6 chances of rolling a 6. So he said, I have 1 out of 6 chances. Whoops, let's get our pen out. 1 out of 6 chances. And he said, so if I roll 4 times, if I times that by 4, then I've got 4 out of 6 chances, which is like 67%. Which is pretty good odds right there. That's absolutely not true. That's not how you do the math, but the real math, he actually had a chance of rolling a 6 52% of the time. And because that was higher than him not doing it, over the long run, it worked out in his favor. But here's the problem, all right? So example 1 is asking us to look at this theory, okay? If you have a 1 in 6 chance of rolling, and if we say that if I roll 4 times, that means I would times this by 4, so I have 4 out of 6 chances. If I were to extend that idea to, well, what happens if I roll 6 times? Well, if I have a 1 in 6 chances and I roll 6 times, his theory says that you are guaranteed 6 out of 6. You will 100% get a 6. Now, I don't know how much rolling of dice you've done in your life, but I am willing to bet that I could roll a dice 6 times and absolutely not get a 6 one of those times. So there's some problems with his logic, and this is actually what kind of led some of the math going into probability. He actually reached out to a mathematician, and they started working together to kind of figure out what the chances of something happening were. And here's some of what they came up with, and people since then have come up with. This and probability, okay? And this is going to kind of lead us into what he should have looked at. So if 2 events are independent, so that means that one event does not affect the other event. For example, if I was going to roll a dice and flip a coin, it doesn't matter what I roll. When I flip a coin, they are 2 completely different events. One doesn't affect the other. In this case, when our con man would roll a dice, just because he rolled a 2 on his first roll, that doesn't affect his second roll. His second roll, he still has the same chance of getting a 2 as he did the first time. So these are called independent events. So if we are considering 2 independent events and the probability that they are both going to happen, we take the probability of one of them happening and multiply it by the probability of the other one happening. Okay, so this principle, we can extend it to any number of events. So I can say, what's the probability of getting a 6 and then a 6 and then a 6 3 times in a row? Or what's the probability of flipping heads on a coin, getting a 6 on a die, and picking a ace from a stack of cards? You just find the probability of each event and multiply them together. Okay, so 3 coins. Suppose you toss 3 fair coins. What's the probability of getting tails all 3 times? Well, the chances of getting tails the first time is 1 out of 2. The chance of getting tails the second time is also 1 out of 2. The chance of getting tails the third time is also 1 out of 2. So when I times those together, I have 1 out of 8 chances. I have a 1 in 8 probability of getting 3 tails, 3 in a row, which happens to be the same probability of getting 3 heads, or getting a heads, tails, tails, or a heads, heads, tails. Example 3, what's the probability of rolling 3 6s in a row with a single fair die? So my first chance of rolling a 6 is 1 out of 6. My second chance of rolling a 6 is 1 out of 6. My third chance of rolling a 6 is 1 out of 6. So when I times those together, I have a what? 1 out of 6 times 6 is 36. 36 times 6 is, nope, not times 3, times 6. 216. So I have 1 out of a 216 chance of getting a 6, 6, 6, which is actually the same probability of getting anything else. The probability, what's the probability of getting a 3 and then a 4 and then a 5? Well, I've got 1 out of 6 chances of getting a 3, 1 out of 6 chances of getting a 4, 1 out of 6 chances of getting a 5. So I have 1 out of 216 chances of getting a 3, 4, 5. Any combination has the same probability because all of them have the same chance of rolling 1 out of 6 times. All right, number 4. The probability that a 100-year flood, so a flood happens once every 100 years. So I've got 1 out of 100 chances. It'll hit the same city in 2 consecutive years. So 1 out of 100 times 1 out of 100 equals 1 out of 10,000. So I've got 1 out of 10,000 chance. Or if you wanted these as decimals, I don't know why you would. I like, oh, come on. 1, 0, 1, 2, 3. That would be what? 0.0001 chances. That's a probability. So that would be what? 0.01%. It's not very likely, right? To get 2 of them in a row. Now, what happens if the first event affects the second event? And this purple box, I put it up here because it's the way the book is going to give it to you on your Get Help button. But if one event does affect the other, then we have to be a little bit more careful about how we find these events. So we would take the probability of the first event multiplied by the probability of the second event, given that the first event happened, which sounds like, huh? So putting that into perspective. Example 5, the game of bingo involves drawing labeled buttons from a bin. There are 75 buttons and you don't replace them. When you draw one out, you don't put it back in. That makes this dependent. If you put it back in, it wouldn't matter what you drawed the first time. There are 75 buttons, 15 B's, I's, N, G's, and O's. What's the chance of drawing? What are the probability of drawing 2 B's on the first 2 selection? Well, my first selection, I have 15 out of 75 chances of getting a letter B. My second draw, because I didn't put that B back in, I've only got 14 B's left. And I don't have 75 total anymore. I have 74 total because I didn't put it back. So I've got to do 15 over 75 multiplied by 14 over 74. So I would do 15 over 75. And I'm going to make sure that I put these in parentheses because if I don't, watch what happens. So that was supposed to be a divide. It helps if I use the right buttons. So there is a 0.0378 chance. That's my probability, 0.0378. Now, if I had forgot the parentheses, if I had done 15 divided by 75 times 14 divided by 74, look what happens. In this case, I get the same numbers. Depending on your calculator and the order that you put them in, we've got to be really careful because this is going to follow the order of operations. When we're using our multiplication and division, it works the same from left to right. Where we're going to get into trouble, and we're going to run into this in just a little bit, is we're not going to be multiplying our probabilities, we're going to be adding probabilities together. So you've got to be careful that you put these parentheses around just to keep your calculator safe and make sure that it's going to actually do things in the right order, okay? So even though it works some of the time, our calculator is not always going to do what we want it to do if we don't separate things out. So make sure that your probability, this 15 over 75, make sure that you put that in parentheses before you start combining these probabilities together, okay? Example 6, a 3-person jury is selected at random from a pool that has 6 men and 6 women. What's the probability of selecting an all-male jury? So we're going to select 3 people. And my chance of getting a male is 6 out of 12 chances, my first time. But I've already selected 1 male, so there's only 5 men left out of 11 people that are left. And then my third choice, if I were to pick a man again, I would only have 4 men to choose out of, and there would only be 10 people left. So I would have to do 6 over 12 times 5 over 11 times 4 over 10. So you would want to do 6 over 12 times 5 over 11 times 4 over 10, which is going to be negative 0.1727272727. Now, sometimes you can turn this into a nice fraction. Like if I hit math, enter, enter. If it can be a fraction, it'll turn it into one for me. So negative 19 over 110. Negative, why did we get a negative? Oh my heck, I'm pushing wrong buttons everywhere. This is what happens when you try to do math quickly. This is a multiply. All right, 0.0909090909. That sounds a lot better. So if I do math, enter, enter, it's going to give me 1 out of 11 chances. That didn't, 1 out of 11, okay? And because I'm multiplying integers on top and integers on bottom, I should get a nice fraction every time. You shouldn't be getting ugly irrational numbers because you're multiplying a rational number by another rational number. So you should usually end up with something nice, okay? Okay, a few more situations. Either or. So we got to be careful. If 2 events are not overlapping, then if we're giving a situation that says, what's the probability of this happening or this happening? So for example, suppose you roll a single die. What's the probability of rolling either a 2 or a 3? Now, the reason these are not overlapping is you can't roll a 2 and a 3. That's impossible. So these don't overlap. You can roll a 2 or you can roll a 3, but you can't do both. So all I have to do is take the probability of rolling a 2 and add it to the probability of rolling a 3. So my chances of rolling a 2, my probability is 1 out of 6, and I'm going to add the probability of rolling a 3, which is also 1 out of 6. So that adds up to be 2 out of 6, which adds up to be 1/3, would be my probability. 1 out of 3 chances that I roll either a 2 or a 3, okay? Now, where this starts, where we've got to be careful, when they don't overlap, it's that simple. You just add the probabilities together because one is not going to affect the other one, okay? But in a situation like this, look at these cards. If I wanted to know what's the probability of getting a queen or getting a club card. Well, my chances of getting a queen, there are 4 queens out of 52 cards. My chances of getting a club, there are 13 clubs out of 52 cards. So I would add those together. But this card right here, oh, I can't even see that blue. This card right here is a queen and it's a club. So I counted it in this probability and I counted it in that probability. I counted it twice. So I have to subtract that probability of getting that one card. So I've got to take the 4 out of 52 queens plus the 13 out of 52 clubs but then I've got to minus the 1 out of 52 chances of getting a queen that is a club. So 4 out of 52 plus 13, that's 17 minus 1. So that's 16 out of 52 chances, which, what did we decide that simplified to? 4 out of 13. So I've got a 4 in 13 chance of getting a queen or of getting a club. Don't forget to minus that one that happened twice. Okay, so to expand on this, because I will use this example in a minute, but I just don't like it as much. So let's move it down here. Let's expand on this idea a little bit more. What's the probability? What's the probability of getting a red card or a 5? Okay, the probability of getting a red or a 5. Well, there are 26 red cards out of 52 cards. And there are 4 5s out of 52 cards. But there are 2 cards that are red and 5s. There's 2 red 5s. So I counted those ones twice. So I've got to subtract them. So 26 plus 4 is 30, minus 2 is 28 out of 52, which is going to be 13 over 7. So I've got 7 out of 13 probability of getting a red or a 5 because they overlap. All right. So if I were to ask, what's the probability of if I'm still picking cards, what's my chance of getting a queen or of getting a 5? Well, queens, I've got 4 out of 52 queens, and I've got excuse me, that's bad math right there. I've got 4 out of 52 5s. But do I have anything that's a 5 and a queen? I don't. So there's nothing I have to subtract because nothing is both. So I get 8 out of 52, which becomes 2 out of 13 chances. A 2 out of 13 probability of getting a queen or a 5. So that's the difference between overlapping. If they overlap, if you count something twice, you've got to subtract how many times you counted it twice, or how many you counted twice, okay? All right, so example 8, so that we can say we used it. There's 8 people in a room, 2 Democratic men, so 2 Democrats that are men, 2 Republicans that are men, 2 Democrats that are women, and 2 Democrats that are, 2 Republicans that are women. What's the probability that you will select either a woman? So what's the probability of a woman or a Democrat? Well, 4 out of 8 of them are women, and 4 out of 8 of them are Democrats. But 2 of the 8 people are both. They're women and Democrats. So we counted them twice. So 4 plus 4 is 8, minus 2 is 6. So I have a 3 in 4 chance, or a 0.75 probability of selecting a woman or a Democrat, because I had to subtract the ones that were both. So be careful about our or problems, okay? All right, the at least once rule. And the math on this one gets a little bit messy. Sometimes the formula is easier to think about than what you're doing. But suppose if we look at this example, what's the probability of getting at least 1 heads when you toss 3 coins? What's the chance of getting at least 1 heads when you toss 3 coins? So my formula tells me that I should take 1 minus the probability of not getting a heads. Well, my probability of not getting heads is getting a tails. So getting tails is 1 out of 2 chances. And then it says to raise that probability of not getting heads to the n, which is how many times you're going to do this. Well, I'm going to flip what does it say? I'm going to toss 3 coins. So this becomes 1 minus 1/2 to the 3rd power. So that's 1 minus 0.5 raised to the 3rd power. So I have a 0.875, and if I want to turn that into a fraction, math, enter, enter, I've got 7 out of 8 probability, or a 0.875 chance of getting at least 1 heads. So you take 1 minus the probability of it not happening once, raised to the power of the number of trials that you do. Okay, so another example. I think the examples are a lot better than trying to decipher the purple box. You purchase 10 lottery tickets. The probability of winning some type of prize is 1 in 10. So what is the probability that you will have at least 1 winning ticket? All right, so 1 minus, what's the probability of not winning? So the probability of not A. Well, A is winning, so the probability of not winning is 9 out of 10, right? You have 1 out of 10 chances of winning, so you have 9 out of 10 chances of not winning, but I bought 10 tickets, so I'm going to raise that to the 10th power. So I'm going to do 1 minus 9 divided by 10 raised to the 10th power, which gives me, again, we can turn this into a fraction. Well, maybe not so much. Well, it probably would if we kept going, but this tells me I've got a 0.651 chance of getting at least 1 winning ticket. Okay, I've got a 0.651 chance of getting at least 1 winning ticket. So that's better than half. Hopefully you're winning more than your $1 that you're losing, right? Okay, homework. What are we on? Homework 7B is where we're at. If you have time to work on at home, please do so. If not, go ahead, bring it to school. We will work on it in class together if we need to. I'll answer questions from the homework, and we'll expand on this idea just a little bit.